Hello, this is Dr. Dave Gaitros for CDA 3100. We're going over flip-flops today. Now, flip-flops are kind of interesting. Inside a computer, we can pass bits around from circuit to circuit, but unless we do something to preserve that 1 or 0, it's lost in the transition. So we have to have some mechanism to preserve a state. In other words, once we turn a bit on, we should be able to keep it on. And that's done by things called flip-flops, and I'm going to build one for you right now. This is actually called just a regular flip-flop, and we'll explain the differences in some of them in a little bit. And I'm going to use a NOR gate to do this, and we usually use either NOR gate or NAND gates to build these. So I need two NOR gates, and I'm actually going to modify this one. And I'm going to make it have 2 data bits instead of just the 5 that comes with it, and I'm going to copy it and paste it. And I did a Control V and a Control C for those of you who are doing it along with me. I'm going to go ahead and put the states on the outside here, and I do that with I'll just use an LED to make them show up. Okay, an LED right there, and I'm going to change the colors. I don't like the colors that come with it, so on color shall be green, and the off color shall be red. Very good. And again, I'm going to do a Control C to copy and Control V to paste, and I'm going to put that one down here and go ahead and make the connections. While I'm doing this, I'm going to go ahead and label them. I'll go up to this one. I'm going to label this one as Q. Q, and I'm going to put the label out to the east, and you'll notice I've labeled the directions out here. I'm going to label this one Q naught. Q as an apostrophe is Q naught, and again I'm going to put the label out to the east on this one. So those are the basic gates, and now I've got to connect them up. So what I'm going to do over here is I've got to put what's called a set and reset, a pin on them. So I'm going to go over here and put a pin, and I'll put the pin right here. I'm going to do a copy and paste and put another pin down here. This pin down here at the bottom of the opposite the Q naught is going to be called S, and we'll label it as such. We'll say this one is S. The label is facing west already, so that's fine. And we're going to call this one R. And this stands for set and reset. So the theory is that whenever we set the flip-flop, Q turns to 1 and Q naught turns to 0. When we do a reset, then Q will turn to 0 and Q naught will turn to 1, the opposite of it. Well, let's go ahead and line these up. Well, obviously I'm going to make this one go here, and I'm going to make this one transition to that one. Now this is what makes a flip-flop work. What happens is the electricity, or the current, is continuously flowing back into the circuit inside it, and this is what actually keeps everything alive. So we're going to put this one up here, and this goes back in like that. Alright, very good. Now then, let's go ahead and turn our probe on so we can test it. And I'm going to turn these both to zeros, and you'll notice that when I do set is to 1, S, this turns to a 1. I turn this off and I turn this one to a 1, okay, you'll see that then Q becomes a 1 and 0 becomes 0. That's the reset version of it. Now here is the truth table of what it looks like in reality, and we'll move this up here so you can see it. You'll see that when both S and R are zeros, Q will be 1 and Q naught will be 0, the opposite. You'll see that there's always the opposite right here. And excuse me, this is wrong right here. Okay. Let me put these the way they were. So what we have here is put these. Whoops. right there is that when both S and R is 0, after S has been 1 and R is equal 0, then there will be 1 and 0 as the Q and Q naught. If they're both 0 and the opposite is true, then what we'll do is after S is equal to 0 and R is equal to 1, then it'll switch back and forth. It's kind of a state reversal is what it is. This is the basis of a flip-flop right here. And what I'd like you to do for this particular exercise is build this and look at that state transition table and just go through and play with these and make sure that it all works out just exactly like you think it should, and play with those things on and off. Build this one, get it to work, and save it. And now what we're going to do is we're going to go on to the next item, which are clocked flip-flops. We'll explain those a little bit. One further note, we can actually change these with, we're using NOR gates for these. We can actually use NAND gates too, and then if you want to, let me go ahead and show you that. I'll show you NOR gates. I'll take this one out. I'll delete that. I'll delete this. And I'll go and put NAND gates in here. I'll put NAND gates, and I'm going to change the input numbers to 2, 2, and I'm going to go ahead and put those up here. Here we go. I'm going to copy that. Okay. Now I have to do something else here. The other thing I have to do is R and S are now reversed. Okay, so this label would actually become S, and this would actually become R, uppercase R. Let me change that one again. Okay, now let's go ahead and do the simulation and show you what happens. So when I do a set right here, you'll see that now that turns the Q on to 1. Let me turn this one off. And whenever I turn this one on to 1 and this one to 0, it's just the opposite. So whenever I use NAND gates, the R and S are actually reversed, or the Q and Q naught aren't reversed. And actually, so that is actually one built with. And let me go ahead and change the text up here. This one's actually built with AND gates. So let me document that. Oops, spell it right. AND gates. Alright, that's a basic review of flip-flops, and it's important that you review this one and actually build the circuits before we go on to the next one. We're going to look at clocked flip-flops. Hope you enjoyed this. Looking forward to doing the next one.